In this video, we will take a look at a second-order differential equation on a series RLC circuit. Our goal is to derive the second-order differential equation in a standard form for the voltage across this capacitor and to solve that differential equation using the initial conditions for the circuit. So let's get started. So here's our circuit. At time t equals 0, the switch is closed. A 10 volt source powers a 1 kilo ohm resistor, 2 Henry inductor, and a 0.5 microfarad capacitor. So on this circuit, by applying Kirchhoff's voltage law around this loop, we can say that the voltage source 10 volt is equal to the voltage dropped between the resistor, the inductor, and the capacitor. So at time t equals 0, switch is closed, the circuit is complete, and by KVL we can say Vn equals Vr at time t plus the inductor voltage and the capacitor voltage. Now the input voltage is given as 10, PR is IR, VL is LDI dt, and we want to leave VC because that's what we're interested in. So we're interested in figuring out what is the voltage across the capacitor. We know that the voltage across the capacitor, the current going through that capacitor is the same current as IT. So the current here is the same. So current going through a capacitor can be written as C dV dt. So let's replace every IT with C dV dt. Now we have second order differential equations because of there's d square dt square. So we have a second order differential equation with Vc. This is not yet in a standard form because the standard form has the second order term has a coefficient of 1. In order to bring this differential equation into a standard form, let's divide both sides by LC to make the coefficient of the second order term 1. So let's do that. And we get a standard form differential equation, d square v dt square plus r over l dv dt plus v over lc equals 10 over lc. Now this equation is in a standard form. R over L is the 2 zeta omega n term, where zeta is the damping factor, and 1 over LC right here is omega n square, which is the undamped natural frequency square. Omega n is undamped natural frequency. The right hand side is 10 over LC. That is the forcing function. Since the circuit has since the circuit has a homogeneous and a particular solution because of the forcing function on the right hand side, we'll have to consider the voltage across the capacitor as both a particular and a homogeneous solution. But before we do that, let's figure out whether this differential equation has a underdamped response, a overdamped response, or a critical damped response. To do that, let's figure first out the natural frequency, omega n. So we can write down omega n is square root of 1 over LC in this case, and L is 2 Henry, C is 0.5 microfarad, so 0.5 10 to the power minus 6, and if we calculate that, it comes out to 1000 radians per second. So that's omega n. Now we have omega n, so let's figure out 2 zeta omega n. 2 zeta omega n is equal to R over L. That basically means zeta is equal to 1 over 2 omega n times R over L, and by plugging in the value of omega n and R over L, we get zeta to be 0.25. Now clearly zeta is less than 1, so the system is going to have an underdamped response. So the homogeneous part of the voltage across the capacitor will give us an underdamped response, and because we have a forcing function that's non-zero, in other words we have a forcing function 10 over LC in this case, our voltage across the capacitor will have a particular solution as well. So we can write down the voltage across the capacitor as the sum of the particular solution and the sum of the homogeneous solution. So let's figure out what the particular solution is. The particular solution is basically the forcing function divided by omega n squared. So we have 10 over LC divided by omega n squared. We already calculated omega n as 1000, so that gives us 10 volt total. So the particular solution is 10 volt. Now the homogeneous solution is because of zeta less than 1, we'll have an underdamped response, and that takes the form of VC homogeneous is equal to K1 cosine omega dt plus K2 sine omega dt, and the whole thing is multiplied by e to the power minus t sigma. Okay? This is the homogeneous solution. K1 is unknown, K2 is unknown, omega d is currently unknown, and sigma is unknown. So let's figure those out. Okay. So in order to figure that out, we need to write the VCT as sum of particular and the homogeneous solution. So let's now figure out what K1, K2 are based on their initial conditions. Now, what are the initial conditions in the circuit? At time t equals 0, the switch is just closed, so the voltage across the capacitor cannot change abruptly. So we can safely say that the voltage across the capacitor at time t equals 0 is the same as the voltage across the capacitor just before t is 0. At t equals 0, the switch was closed, and before t was equal to 0, the switch was open. There was no power source, so the voltage across the capacitor is equal to 0. So voltage across the capacitor at t equals 0 is equal to 0. Similarly, the current across the current through an inductor cannot change abruptly. So again, at t less than 0, the switch was open. There was no current flowing through the circuit. So we can safely assume that the current t less than 0 is 0. And since the current through an inductor cannot change abruptly, we can safely say that the current through the inductor at time t equals 0 is equal to what it used to be before t is 0, and that's equal to 0 amps. Using these two initial conditions, we can now figure out what K1 and K2 are. So let's start with the voltage across the capacitor. Applying the initial condition for the capacitor voltage at time t equals 0, let's put in t equals 0 in this expression right here. So Vc0 equals 10 K1 cosine omega d0, K2 sine omega d0, e to the power minus 0 sigma. This leads us to cosine 0, sine 0, e to the power 0. Cosine 0 is 1, sine 0 is 0, e to the power 0 is 1. And simplifying that, we get 10 plus K1 is equal to 0. In other words, K1 is equal to negative 10. So we figured out what K1 is by using the initial condition for capacitor voltage. Now let's take a look at K2. For that, we'll use the initial condition for the current through that system. Now, applying initial condition for t equals 0, but before that, we need to figure out what IT is. So I is C dV dt, so we need to take the derivative of that. So here is C dVt was 10 plus K1 cosine omega dt plus K2 sine omega dt e to the power minus t sigma. So if we take that derivative, we'll get, of course, in this case, we do derivative of 10 with respect to t, and in here we have cosine omega d e to the power minus t sigma, so we need to do derivative by parts. Again, for the second part here, we have sine omega dt e to the power minus t sigma, so we again do derivative by parts right here. So after doing the derivative, d10 over dt, since 10 is a constant, we get 0. We did the derivative of cosine to get sine, sine to get cosine, and so forth. So here's I of t after we are done taking the derivatives. Now at time t equals 0, let's plug in all t to be 0. So I of 0 equals all t's set to 0. Sine 0 is of course 0. Cosine 0 is of course 1. So let's plug that in. So we end up with 0, since I of 0 was 0, equals capacitor C K1 minus sigma plus K2 times omega d. So this is what we get. Now sigma and omega d come out to be 250 and 968.25, and that's calculated by sigma is zeta omega n. Omega d is omega n square root of 1 minus zeta square. and that is 968.25. So that's where we get 10 times 250, 968.25, and that leads us to K2 equals negative 2.58. So our voltage across the capacitor is now 10, that's because of the particular solution, minus 10, that's K1, cosine omega dt, minus 2.58 sine omega dt, e to the power minus t over sigma. So if we plug in the value of sigma and omega d, we've solved the voltage across the capacitor. So, started out with a circuit where the switch was open at t equals, and at t equals 0 the switch was closed. The standard differential equation, second order differential equation in terms of the voltage across the capacitor was d square v dt square plus r over l dv dt plus v over lc equals 10 over lc. Because of the forcing function, our solution had both a particular and a homogeneous solution. We calculate zeta to be less than 1, leading us to a underdamped response. And we figured out that the voltage across capacitor is a particular solution and the homogeneous solution. By plugging in initial conditions, we found the values of K1, K2, and omega d and sigma. So our final solution is VCT equals 10 minus, taking the minus out, 10 cosine 968.25t plus 2.58 sine 968.25t e to the power minus 250t volts.